A global game server and a global video library look identical on a whiteboard. Same edge, same arrows. But the game speaks raw UDP and needs a fixed IP, while the video is cacheable HTTP. Pick the same service for both, and one of them quietly breaks. Episode 28 of Cloud Architect Path starts now. By the end of this video, you'll be able to tell instantly whether a scenario wants CloudFront, Global Accelerator, or a hybrid link back to your own data center. These services look nearly identical on a diagram, but they solve genuinely different problems, and one word in the requirements usually decides which is right. In the last episode, Megacorp's buyers in Australia and Japan were hitting a Singapore origin, and tail latency climbed past 900 milliseconds. We put CloudFront at the edge to serve cached supplier PDFs and product images close to those users. And we flagged that CloudFront and Global Accelerator both stored at the edge, but do very different jobs. Now let's pull those two apart properly, and then add the connection back to your own data center. Let's lock in 5 terms you'll hear throughout. An anycast IP is a single address announced for many edge locations at once, so each user automatically reaches the nearest one. A signed URL is a time-limited signed link that grants temporary access to one specific CloudFront file. Lambda at Edge runs Lambda functions right at the edge locations, inspecting and modifying requests close to the user. Direct Connect is a dedicated private fiber link from your data center to Amazon Web Services. And site-to-site VPN is an encrypted tunnel from your network to Amazon Web Services over the public internet. Caching solves repeated reads beautifully, but it doesn't touch everything. That first byte still has to cross the network, and for anything that can't be cached, every request crosses it. Between Singapore and Sydney, packets hop across congested, unpredictable public networks, and the path itself adds latency. Amazon Web Services gives you 2 edge services that attack this from opposite directions. One stores copies of your content close to users. The other speeds up the path itself. Choose the wrong one, and you'll build a diagram that runs perfectly while solving the wrong problem. Here's the mental model to carry through the whole episode. CloudFront is like a chain of local warehouses, each stocked with copies of your popular content. When someone orders, the nearest warehouse ships it instantly, never touching the central factory. Global Accelerator is different. It builds a private express highway that always connects you to the factory over the fastest, least congested road. Nothing is stored along the way, it just makes every trip faster. CloudFront is a content delivery network, and it caches HTTP and HTTPS content at over 750 points of presence, spread across more than 100 cities in over 50 countries. It serves static files, dynamic responses, video streams, and API responses from the cache nearest each user. Because a cached hit is served locally, you eliminate the round trip to the origin, which cuts both latency and the load on your source. But hold on to one boundary. CloudFront works only with HTTP and HTTPS. Nothing else. CloudFront caches in 3 tiers. Closest to the user sits the edge location, and there are over 750 of them. If the content is there, the user is served instantly, and the origin never hears about it. Behind those sits a smaller set of 15 regional edge caches. So when a nearby edge doesn't have your long-tail content warm, the request checks a regional cache before ever reaching your origin. And only when both miss does a request travel all the way back to the origin. The payoff is that even rarely requested content usually gets served from something closer than your source. CloudFront can also lock content down, and there are 2 ways to do it. A signed URL is like a time-limited concert ticket. It grants access to one specific file for a specific window, stamped with a signature that can't be forged. That's your pick for a single movie rental or a software download. A signed cookie carries the same kind of policy, but it's delivered through set cookie headers, and it grants access to many files at once. Reach for that when you want to open a whole subscriber area of a site without rewriting every URL. Per file, signed URL. Section-wide, signed cookie. Here's the part people miss. A signed URL only enforces access at the CloudFront layer. If your S3 bucket still allows public access, someone can skip CloudFront entirely and fetch the object straight from the S3 URL. Your signature protected nothing. The fix is origin access control, which configures the bucket so it only accepts requests coming from CloudFront service principal. Signed URL plus OAC is the complete pattern. Signed URL alone leaves a side door wide open. CloudFront can run your code at the edge too, and there are two flavors. Lambda Edge is the powerful one. It runs at all 4 hooks: viewer request, origin response, and viewer response. It can make outbound network calls, and it supports both Node.js and Python. Just remember, you must author those functions in the US East 1 region, no matter where your origin lives. CloudFront functions are the lightweight option. They run only at the viewer hooks. They're JavaScript only with no network access, but they're sub-millisecond and far cheaper. Since November 2024, they can also modify origins, so many simple Lambda Edge patterns can now move to the cheaper option. CloudFront also has its own kind of resilience. You define an origin group holding a primary and a secondary origin. If the primary returns a 500, 502, 503, 504, or simply times out, CloudFront retries the same request against the secondary. Those are the default trigger codes. You can also configure additional 4XX codes like 403 to trigger failover, but that requires explicit setup. And this all happens inside a single viewer request. It's a per request retry at the CDN layer. Keep that boundary clear in your head. This is not network level rerouting, and it's not DNS failover. It's CloudFront quietly trying a backup origin before it gives up on one response. Quick recap before we switch services. CloudFront is a content delivery network that caches HTTP and HTTPS content at the edge. You restrict access with signed URLs for a single file, or signed cookies for a whole section. For edge compute, Lambda Edge handles complex logic, while CloudFront functions handle simple, fast transforms. And origin failover retries a secondary origin inside one HTTP request, triggered by default on 500 range errors and timeouts, with optional 4XX codes configurable on top. Every one of those is an HTTP story. Now watch what changes when the traffic isn't HTTP at all. Global Accelerator gives you 2 static anycast IP addresses announced from the Amazon Web Services Edge network. Traffic enters Amazon Web Services at the nearest edge, then rides the private Amazon Web Services backbone to the best regional endpoint. It works with any TCP or UDP protocol, not just HTTP, and it runs continuous health checks. With default settings, a 30-second check interval, and a threshold of 3 consecutive failures, rerouting can begin anywhere from 30 to roughly 90 seconds after a failure is detected. You can tighten that window significantly by reducing the interval and threshold. Here's the crucial part. It caches nothing. It doesn't remove the round trip to your origin the way CloudFront does. It just makes that round trip faster and more reliable. The Global Accelerator Developer Guide draws the line cleanly. It says Global Accelerator is a good fit for non-HTTP use cases, such as gaming over UDP, Internet of Things over MQTT, or Voice over IP. And it adds, for HTTP use cases that specifically require static IP addresses or deterministic fast regional failover. Read that back and you've got the entire decision rule in one sentence. Non-HTTP FTP protocols, a fixed IP requirement, or fast failover. Any one of those points at Global Accelerator. Think of those two static IPs like a single phone number for a national chain. No matter which city you call from, the network connects you to the nearest branch automatically. And the number never changes, even if branches open or close. That's anycast. The same IP is announced from many edge locations, and the internet's routing quietly steers each user to the closest one. Your devices hardcode two addresses that stay fixed for the life of the accelerator. Follow one packet through Global Accelerator. The user starts by connecting to one of the two static IPs. That traffic enters Amazon Web Services at the nearest edge location, the closest point where those anycast addresses are announced. From there, it stops using the messy public internet and rides the Amazon Web Services private backbone to the optimal regional endpoint. That endpoint can be an application load balancer, a network load balancer, an EC2 instance, or an elastic IP. The backbone stretch is where the win lives, a consistent low-latency path that the public internet simply can't promise. There are two accelerator types, and the distinction matters. The standard accelerator load balances to healthy endpoints and does health check failover with default settings that can take anywhere from 30 to roughly 90 seconds. But you can tune the interval and threshold down to make it much faster. It supports application and network load balancers, EC2, and elastic IPs. That's your general purpose choice. Custom routing is the specialist. It deterministically maps port ranges to specific EC2 instances, so you can send a particular user to a particular server. That's exactly what multiplayer game matchmaking and voice-over IP session routing need. The catch is that custom routing does no health checks and no automatic failover, so your application has to manage endpoint health itself. Here's a mistake that shows up in the real world. Someone puts Global Accelerator in front of a file download expecting the same speed up CloudFront gives, and they're disappointed. A community benchmark from Japan and the US to an Ireland origin captured it well. CloudFront cut download time by roughly half through edge caching. Global Accelerator barely moved it. That's not a failure, it's the design. CloudFront eliminates the origin round trip by caching. Global Accelerator keeps the round trip and just makes the path faster and more consistent. So here's the decision, and it's a single fork. Ask one scenario. Is the content cacheable, HTTP, or HTTPS? If yes, the phrase to listen for is cache web content globally, and the answer is CloudFront. If no, meaning the protocol isn't HTTP, or you need static IPs, or you need failover in under 30 seconds without waiting on DNS, the answer is Global Accelerator. Almost every scenario resolves on that one scenario. Get the protocol and the qualifier straight, and the service picks itself. And these two aren't rivals. Amazon Web Services published a real SAP Fiori rollout that used both at once. CloudFront accelerated the Fiori interface because the HTML, JavaScript, and CSS assets are cacheable. Global Accelerator handled the OData API calls because external integration systems needed a static IP to allow list, and those responses weren't cacheable. Both services even share the same physical edge buildings, but they operate at different layers. So the pattern to remember is simple. One architecture, each service handling the traffic that actually fits it. One quick thing to disarm before it fools you. Both CloudFront and Global Accelerator include Amazon Web Services Shield standard for free, giving you layer 3 and 4D DOS protection automatically. Because both have it, Shield never breaks the tie. If a scenario dangles Shield standard as a reason to pick one over the other, ignore it. The real deciding factors are protocol, caching, and whether you need a fixed IP. So far, we've been speeding up traffic between users and Amazon Web Services regions. Now, flip the problem around. What about the link from your own data center into Amazon Web Services? That's hybrid connectivity, and it's a completely separate question. Amazon Web Services gives you two ways to build that link, and they trade off against each other on performance versus speed of deployment. And for the strictest requirements, you can layer them together. Let's look at both. Direct Connect is a dedicated, private fiber link between your facility and Amazon Web Services, running anywhere from 1 to 400 gigabits per second. It gives you consistent low latency and bypasses the public internet entirely. The cost is time. Provisioning takes weeks to months because a carrier has to lay physical cross connects. And it is not encrypted by default. Site-to-site VPN goes the other way. It builds IPsec encrypted tunnels over the public internet, 2 of them in separate availability zones for redundancy. Standard tunnels support up to 1.25 gigabits per second each. Large tunnels, which require transit gateway, now support up to 5 gigabits per second each. It provisions in minutes to hours, but because it rides the public internet, its performance varies. Picture it this way. Direct Connect is like leasing a private rail line between your office and Amazon Web Services. It's fast, predictable, and yours alone, but it takes months to lay the track. Site-to-site VPN is like driving a locked armored truck on the public highway. You can leave immediately and your cargo is secure, but you share the road with everyone, and your speed depends on the traffic that day. That single image captures the whole trade-off: predictable performance and long lead time versus quick and encrypted with variable speed. This next point catches a lot of people, so let the doc say it plainly. The Direct Connect user guide states that Direct Connect does not encrypt your traffic in transit by default. To encrypt data crossing Direct Connect, you must add a transit encryption option. So burn this in. Private does not mean encrypted. A dedicated link keeps your traffic off the shared internet, but the packets themselves are still in the clear unless you layer encryption on top. If a scenario adds the words, and the connection must be encrypted, Direct Connect alone is not the answer. So, how do you get both private performance and encryption? You combine them. You run the IPsec VPN tunnels over the Direct Connect link instead of over the public internet. If Direct Connect is the private rail line, this is putting a sealed armored container onto that private train. You get the speed and exclusivity of the dedicated track, plus the tamper-evident lock of encryption. Using a private IP VPN over a transit virtual interface even avoids exposing public IPs on the VPN endpoints. That combination is the go-to answer for regulated healthcare, financial services, and federal workloads. The well-architected hybrid networking guidance spells this out. It says you can combine one or more Direct Connect connections with the VPC VPN, and that this combination provides an IPsec encrypted private connection that also reduces network costs, increases bandwidth throughput, and gives a more consistent network experience than an internet-based VPN. So when a question asks for encrypted, private, and consistent performance altogether, that's your composite requirement, and layering VPN over Direct Connect is the pattern that satisfies all 3. Let's round up the mistakes that quietly cost points. First, CloudFront can't handle non-HTTP traffic. No raw TCP, no UDP, no MQTT, no voice over IP, and no gRPC. Those all belong to Global Accelerator or a direct load balancer. Second, CloudFront resolves to a domain name whose IP addresses change. So, if a firewall must allow list a fixed IP, only Global Accelerator's 2 static IPs work. Third, Direct Connect is not encrypted by default. You add VPN or MACsec for that. And fourth, Lambda Edge functions must be authored in the US East 1 region, no matter where your origin sits. One more distinction, because 3 services all offer failover, and they are not interchangeable. Global Accelerator fails over at the network layer in seconds, with no DNS time to live involved, and it reroutes traffic across regions. CloudFront origin failover happens inside a single HTTP request, retrying a secondary origin. And Route 53 health check failover takes minutes because it changes the DNS answer and is bound by DNS time to live. When a scenario demands failover in seconds without DNS delay, that keyword points at Global Accelerator every time. Here are the rules to carry forward. Cache HTTP content globally, that's CloudFront. Non-HTTP protocols, static ICE, or fast failover, that's Global Accelerator. A private, consistent hybrid link, that's Direct Connect. An encrypted internet hybrid link with fast setup, that's site-to-site VPN. And when you need encryption and consistent private performance together, layer VPN over Direct Connect. Match the protocol and the qualifier, and the service falls out on its own. Now, let's put it to the test with a quick 5-question quiz. Question 1. A gaming company runs UDP-based game servers across 3 Amazon Web Services regions. The client firmware must hard-code fixed IP addresses, and player traffic must fail over between regions within seconds if a region goes unhealthy. Which service fits? Option A, Amazon CloudFront with origin failover. Option B, Amazon Web Services Global Accelerator. Option C, Amazon Route 53 latency-based routing. Or Option D, Amazon Web Services Direct Connect with a public virtual interface. Run the decision rule before you answer. This one is B, Global Accelerator. Look at the 3 signals stacked together. The protocol is UDP, so CloudFront is out immediately. The firmware needs fixed IPs, which only Global Accelerator's 2 static anycast addresses provide. And failover in seconds without DNS delay is exactly what its health check rerouting delivers. Route 53 would be too slow because it's bound by DNS time to live. Question 2. A video service stores its library in S3 with public access blocked. Paying subscribers should get time-limited access to individual video files, and users must not be able to fetch the content directly from S3. What combination achieves this? Option A, signed cookies plus a bucket policy allowing public reads. Option B, Global Accelerator with a custom routing accelerator. Option C, CloudFront signed URLs with origin access control on the S3 bucket. Or Option D, a site-to-site VPN restricting access to corporate IPs. Pause here if you want more time. The right call here is C. Signed URLs give per file, time-limited access, which matches individual video files exactly. And origin access control is what stops users from bypassing CloudFront and hitting the S3 URL directly. Signed cookies would grant a whole section at once, and a public bucket policy would throw the door wide open, the opposite of what you want. Question 3. A financial services firm needs a hybrid link to Amazon Web Services with consistent low latency and end-to-end encryption to satisfy compliance. Which approach meets both requirements? Option A, Direct Connect alone with a dedicated 10 gigabit connection. Option B, site-to-site VPN alone over the public internet. Option C, CloudFront with HTTPS between origin and edge. Or Option D, IPsec site-to-site VPN layered over a Direct Connect connection. Think about which constraint matters most here. If you said D, well done. This is the composite requirement, encrypted and private and consistent all at once. Direct Connect alone gives the consistent private path, but isn't encrypted by default. VPN alone is encrypted, but rides the unpredictable public internet. Layer the IPsec VPN over Direct Connect, and you get both, which is the standard answer for regulated finance, healthcare, and federal workloads. Question 4. An architect wants to run simple URL rewrites and header normalization at the CloudFront edge at the lowest possible cost, with no outbound network calls needed. Which edge compute option fits best? Option A, CloudFront functions. Option B, Lambda at edge at the origin request hook. Option C, a standalone Lambda function in the origin region. Or option D, Amazon Web Services step functions triggered per request. Lock in your answer before I give it away. It has to be A, and here's why. The work is simple, URL rewrites and header normalization, with no network calls required. That's the exact sweet spot for CloudFront functions, which run sub-millisecond JavaScript at the viewer hooks and cost far less. Lambda at edge is more powerful and can make network calls, but it's roughly 6 times pricier and simply overkill for transforms this light. Question 5, and let's test a concept from an earlier episode. Megacorp's payment partner requires a single fixed IP to whitelist, but the application itself speaks HTTP and needs layer 7 path routing. Which design satisfies both the static IP and HTTP routing requirements? Option A, an application load balancer with a CloudFront distribution in front. Option B, a network load balancer with an elastic IP in front of an application load balancer. Option C, a single application load balancer with a fixed DNS name. Or option D, Global Accelerator custom routing to EC2 instances. Got your pick? Let's see. The answer is B. An application load balancer has no static IP, so on its own it fails the whitelist requirement. That's the outage Megacorp hit when the load balancer's IP changed during a spike. Put a network load balancer with an elastic IP in front, and you get the fixed address the partner needs, while the application load balancer behind it still does the layer 7 path routing. A fixed DNS name isn't a fixed IP, so option C doesn't cut it. Okay, content delivery and network acceleration, CloudFront and Global Accelerator is wrapped. If this made your prep easier, please subscribe. It keeps these free and helps them find more students. Tell me in the comments what stuck with you. Got an exam you want a course on? Request it below. And any feedback on the speed or the visuals? Send it my way. I genuinely use it. See you in the next lesson.